Okay, we are continuing talking about sign chart method to solve quadratic inequality. Let's look at the second problem. It's 2x squared plus x bigger than or equal to 3. I mentioned the focus of this section is the sign chart method. So we are going to only apply sign chart method to solve this inequality. So the first step, we are going to rewrite this quadratic inequality in the standard form. Standard form of a quadratic inequality has a 0 on the right-hand side and has a quadratic trinomial on the left-hand side. That's step 1. Step 2, we are going to factor the quadratic trinomial on the left. Yeah, I know it's a quadratic trinomial with the leading coefficient different from 1, 2x squared plus x minus 3. So what method we could apply to factor this quadratic trinomial? Slide, divide, slide method, right? We slide 2 to be with negative 3. We construct or create a new quadratic trinomial with leading coefficient 1. That is x squared plus x minus 6. And then factor this quadratic trinomial with leading coefficient 1. We have which two numbers? Which two numbers multiply to negative 6 add up to 1? You know that, right? 3 and negative 2. 3 times negative 2, negative 6. 3 plus negative 2, positive 1. And then we're gonna divide the two numbers. The two numbers we have just found by the original leading coefficient 2. Right after we divide, we're gonna reduce. Yeah, so x plus 3 over 2. This is x minus 1 because 2 over 2 is 1, right? And another slide. After we reduce the fraction, we still have a denominator here. So we're gonna slide it back. Okay, slide it back. You would have 2x plus 3 times x minus 1. However, because we are not actually factoring a quadratic trinomial, we are going to apply this. We are going to rewrite the trinomial on the left-hand side as give me 1 second. X plus 3 over 2 times x minus 1. Okay? It won't change anything because it is an inequality. If you divide the whole inequality, every term by 2, you would have this inequality. They are equivalent. Okay? They are equivalent. And this form is more convenient. If we let P of x be the trinomial on the left, then P of x would be x plus 3 over 2 times x minus 1. The trinomial is in the factored form. X plus 3 over 2 times x minus 1. Okay, so P of x has 2 zeros. I explained what is a zero of function earlier, right? The 2 zeros are negative 3 over 2 and a positive 1. Negative 3 over 2 would make this factor be 0. And a 1 would make the second factor be 0. So the function P of x has 2 zeros. The 2 zeros would divide the whole real number line. Why do we consider the whole real number line? Because the domain of the function, of the quadratic function, is the whole real number line. We'll divide the whole real number line into 3 parts. So this is a negative 3 over 2. This is 1. Part 1 is from negative infinity to this number. And this time we're going to use closed interval. I'll explain why this time we use closed interval. Second part is from negative 3 over 2 to 1. The part 3 would be 1 to positive infinity. Okay? And the 3 intervals gonna be the first row of the chart. Again, we are applying sign chart method to solve this inequality. Now I'm gonna make the chart. First interval, negative infinity to negative 3 over 2. Left open, right close. Negative 3 over 2 is in the interval. We include negative 3 over 2 in the interval. And second interval is also closed. Negative 3 over 2 to 1. Third interval also closed, 1 to positive infinity. Why do we consider the two zeros here? In previous example, we use open interval, right? How come here we use closed? Because if you look at the original inequality, if you look at this one, you would know 3 over 2, negative 3 over 2, and 1, they are in the solution set. They are in the solution set. Because if you plug in x equals negative 3 over 2, you would have 0 bigger than or equal to 0. That's a true statement. If you plug in x equals 1, left-hand side is 0. We have 0 bigger than or equal to 0. It's also a true statement. So we know the two numbers are solutions already. Of course, we include them in the intervals. That's the reason. Okay, let's continue with the chart. Second row, testing point of the intervals. We choose equal to 0, right? Look at here. We're looking for the intervals over the inequality is already in the standard form. When you see one side is 0 and then the other side is already factored, so that's actually ideal form for applying the sign chart method. So we're gonna let p of x be the left-hand side, the quadratic function, x plus 5 times x plus 1. This function has two zeros. The two zeros are negative 5 and negative 1. You understand what is a 0, right? Yeah. When you plug in x equals negative 5 here, you have the corresponding function, the corresponding y value be 0. So negative 5 is a 0 of the function. Same thing, negative 1 plug in here, corresponding y value is 0. So it has two zeros. The two zeros divide the whole real number line into two parts. By the way, negative 5 and negative 1, which one is smaller? You're going to be careful with that. Negative 5 is to the left of negative 1. Negative 1 is bigger than negative 5, okay? The two numbers divide the whole real number line into three parts. Negative infinity to negative 5, negative 5 to negative 1, negative 1 to positive infinity. This time, we exclude the two zeros. We have two circles here, two holes here. Why? I'm going to explain, okay? It's same with example 1. So now I'm going to make my chart. Row 1, I have three intervals. Negative infinity to negative 5 open. Negative 5 to negative 1 open. Negative 1 to positive infinity open. Yeah, why don't we include negative 5 and negative 1? Because we know negative 5 is not a solution. If you plug in negative 5 in the original inequality, you have 0 less than 0. That's a contradiction. We also know negative 1 is not a solution. Same thing, because if you plug in x equals negative 1, you have 0 less than 0. That's a contradiction. Okay, so that's the reason we have the intervals open intervals. Second row. Row 2, testing point, right? Convenient whole numbers or integers. Here, maybe I try -10. This, I choose, how about -2? This one, +10. Any number inside the intervals could be the representative, but you want a number which is very convenient. Okay, row 3, P of x. After you repeat those examples, you would get the idea about the sign chart method. P of x is x plus 5 times x plus 1. Let's see the sign of the function at those testing points. Plug in -10 here. First parenthesis is negative, second parenthesis is negative, negative times negative positive. Plug in -2. We have a positive here, negative here, so negative. Plug in 10 positive. Positive here, so positive times positive. Okay, very good. What are we looking for? We are looking for intervals over which P of x is less than 0. Okay? We are looking for intervals over which P of x is negative. So here we go. That's the solution set, right? Yeah, the solution set is one open interval, which is a -5 to -1. So far so good? Let's see if we can include in example 4 here. I think 20 minutes would be okay. Before, when I make the video very long, the video is compressed. The video is compressed, like half watching time only. That's a big waste. And include this one. 3x cubed minus 7x squared minus 20x less than 0. We are going to solve this inequality. By the way, this inequality is not a quadratic inequality. It is a polynomial inequality. Polynomial inequality. The polynomial inequality is in the standard form because the right-hand side is 0 already. Left-hand side is a polynomial with degree. What's the degree? Degree is 3. So it's not a quadratic, right? Quadratic, we know degree is 2. So this is a little bit a little beyond the scope, but it's good to know, and it would help you to understand the sign chart method. So let's see how do we process this problem. Firstly, we are going to let P of x be the polynomial on the left, 3x cubed minus 7x squared minus 20x, and then I'm going to factor it. All the three terms contain a x, so I'm going to factor x out, and inside the parentheses I would have 3x squared minus 7x minus 20. Inside the parentheses we have a quadratic trinomial, right? Leading coefficient is different from 1. Let's see if we can slide divide slide to factor it. Slide 3 to be with -20. We have x squared minus 7x minus 60. And then we're going to factor this trinomial, which two numbers, 12 and 5 would be okay, right? Do you see that? We have a procedure for the shortcut method. -12, -12, -12, +5. Double check. -12 times +5 gives us -60. -12 plus 5 gives us -7. So, yeah, that's good. And then divide the two numbers by the original leading coefficient 3. And then reduce it. We have x minus 4. 12 over 3 is 4. Here, x plus 5 over 3. And then slide it back. We still have a denominator here. Slide it back in front of x. So we would have x minus 4 times 3x plus 5. So we are able to factor this trinomial as x minus 4 times 3x plus 5. Or actually even better, if you use x plus 5 over 3, that's even better. It will not affect the final result. It will not affect the final result at all, okay? So we could, we can leave this like that. Yeah. So this function, this polynomial function, p of x, has 3 zeros. The 3 zeros are 0, 4. 4 would make the second parenthesis be 0, right? And a negative 5 over 3. Negative 5 over 3 would make the third factor be 0. And those 3 zeros divide the whole real number line into how many parts? 4 parts. Yeah. So be careful with their order. Negative 5 over 3 is here, 0 is here, 4 is here. So the 4 parts. First part, negative infinity to negative 5 over 3, open. Second part, negative 5 over 3 to 0, 0 to 4, 4 to positive infinity. The 4 open intervals gonna be in my row 1 of the chart. 1, 2, 3, 4. So negative infinity to negative 5 over 3, open. Negative 5 over 3 to 0, open. 0 to 4, open. 4 to positive infinity, open. Yeah. Why do we use open intervals? Because we know those 3 zeros do not satisfy the original inequality. Okay, the original inequality has strictly less than. If you plug in those 3 values, you would have contradictions. So we do not include those 3 values in the intervals. That's the reason we have 4 open intervals here. Let me double check. In the first row, we have 4 open intervals. Negative infinity to negative 5 over 3, negative 5 over 3 to 0, 0 to 4, 4 to positive infinity. Yeah, okay, very good. Row 2. Row 2, we pick testing point, any convenient number. 5 over 3 is about negative 1 point something. So, you know, I can choose a negative 10, right? I don't have to choose a negative 2. Negative 10 would be very convenient. And here, I'm going to do negative 1. Okay, negative 1 is inside this parenthesis. Inside this open interval, I mean. Inside this open interval. This one, try positive 1. This one, try positive 10. And the last row, we are going to look at the sign of the polynomial function p of x, which is x times, what is it? X minus 4 times x plus 5 over 3. So p of x right now is a product, is in the factored form, is a product. In x equals negative 10, negative, negative, negative. If we plug in x equals negative 10, all the 3 factors gonna be negative. Negative times negative times negative gives you negative. So far so good. And then we plug in x equals negative 1, negative, negative, positive. And we have a positive here, okay? Because those 2 negative numbers multiply to positive. Positive times positive gives you positive 1. Positive, negative, positive. So we have a negative here. The last one, positive 10. We have a positive here, positive here, positive here. So that's positive, right? So we complete the chart, and we are going to see the intervals over which the function p of x is less than 0. we are looking for the intervals over which P of X is less than 0. Negative, okay? We have 4 intervals. We need to find the intervals over which P of X less than 0, negative, okay? So we have this one is negative, right? And this one. You see what I'm saying? So we have this one is negative, right? And this one. You see what I'm saying? So the solution set of the original inequality is going to be the union of those two intervals. Negative infinity to negative 5 or 3. Union 0 to 4. Okay, so yeah, this is the second part of this section. We practice another 3 problems, sign chart method. I'm gonna stop here and start the part 3 of this section.